We can't design better products if we don't understand the materials they're made from. In this episode, Dr. Carolyn Carta, who we like to call Dr. Cece, breaks down why the scientific method is essential to building responsible, effective hardware, and how consumer fears like all plastic is toxic often distract from what really matters: testing, data, and precision. With a career spanning conservation science to sustainable manufacturing, Dr. Cece brings a unique voice to the materials conversation, one that's radically practical and refreshingly unafraid to challenge popular narratives. Today's guest is a scientist, educator, and startup whisperer who's made a career out of asking better questions, especially about the materials we touch, drink from, and build with every day. Dr. Carolyn Carta, or we call Dr. Cece, is a materials scientist and the founder of CArtLab Solutions, where she helps early-stage companies make smarter decisions about product design, safety, and sustainability. From animation preservation at Disney to next-gen hardware and packaging systems, Dr. Cece brings both deep lab expertise and a practical, no BS approach to innovation. She's on a mission to bring more scientific method and a lot less greenwashing to how we evaluate materials, risk, and real-world performance. Dr. Cece, welcome to Unbottled.
Thank you for having me.
Absolutely. So one thing I love to do is to start us out, let's have a toast to Kadeya's stainless steel bottles that you're helping us with. Cheers. All right. So before we get into materials, let's ground this in your journey. What led you to science and eventually launching your own firm, CArtLab Solutions?
I love that question because I did not expect to be a founder and have my own business, but I grew up with physician parents, and they always encouraged curiosity from a young age. And because of that, I saw myself as an art kid for a long time. And I kind of accidentally sent the curve on my first chemistry exam in high school and realized, I guess I'm good at this too. And so I ended up studying both chemistry in my master's and material science engineering in my PhD, in art conservation specifically, learning how materials age, fail, and interact over time. And then launching CArtLab Solutions was more about like safety and agency. Reporting multiple workplace safety violations to OSHA and EEOC, with then having my first client paying me directly for material science consulting work, kind of made me see that there was a market opportunity and a gap, and I felt responsibility to fill that space. I was really frustrated in my career reading a lot about recalls, products that really didn't work for everyone. And CArtLab is really all about setting a higher standard here. Rigorous science, safer R&D, and equitable access to expert materials decision-making. So, CArtLab exists because good science and safe work shouldn't be optional in product development.
Amazing. Yeah. And well, we're going to discuss all of this, but just understanding a little bit more about what you do, you start to look around at products and objects around the world and to start to say, well, if someone had been maybe more intentional in the beginning, right, that would lead to better experience, better economics, longevity of the product. So we'll get into all of that. So Dr. Cece, you've worked on everything from, as you mentioned, preserving Disney animation cells, which is amazing. Never even occurred to me that it is a job and a needed activity, but amazing, to 3D printing medical devices. What first pulled you toward material science specifically?
So I had a mentor during my master's when I was studying chemistry, Thea van Oosten, and she was at the Cultural Heritage Institute in the Netherlands. And I was asking her for advice. And she gave me great advice about pivoting from my chemistry focus to material science engineering for my PhD. She mentioned that chemistry tends to be operating in a silo, where material science engineering helps you understand heterogeneous systems, which is really just to say, like, nothing we have is just one material. Right. It's a whole bunch of materials together. So then I could better understand inorganic materials, organic materials, and interfaces all together. And art conservation fights time when we're studying art conservation science. So it's like oxidation, plasticizer loss, embrittlement, whereas products are actually fighting use. So there's still some of those factors that art conservation science is looking at, but it also includes heat, detergent, stress, abrasion, and human behavior. So they're different contexts, but they're really the same physics and ideas.
Yeah, fascinating. Wow. Okay, this is a great conversation. So you talk a lot about bringing scientific method into early stage R&D. Why is that so critical, especially in climate and hardware innovation?
So I always say that to my clients, like when I'm pitching myself to them, is, if you do skip this scientific method at the beginning, you're really not just risking a bad product, you're also risking building the wrong system altogether. So, hardware has a lot of complex constraints. It's not just about having a clear side deck to raise money. It's a lot of different parameters here. So, for example, in your space of like climate and closed loop systems, and even this extends to med tech, which I also serve, they stack constraints on top of each other, and each constraint impacts the next constraint. So it's like performance, safety, compliance, manufacturability, repair, end of life. So in startup terms, the scientific method really is about asking, like, defining what's true, defining how it can fail, running the fastest test that can prove you wrong. Because if you can prove yourself wrong, someone definitely will prove you wrong, and you don't want it to be someone else that's paying you. You want it to be yourself.
Right.
And then tracking those baselines so that the results can mean something in your development. And this isn't just like about bringing an academic theory to product development. It's actually something that regulators do all the time.
So when you talk about, ensuring that you're not going down this wrong path, right? Like I think of the term path dependence. So you're really saying, let's make sure that what you're building is a great foundation for whatever comes next, right? So that everything you're building on top, right? It's not a house of cards, but it's actually a really viable, resilient structure.
Exactly. And one thing that has come up before with some startups I've worked with is they say they have kind of a stepwise way that they're going to approach their product development. And materials many times see after they've already chosen their manufacturer. And I always say, if you've chosen your manufacturer before you know what material, you're going to have to go back and you're going to have to redo that decision potentially.
Right.
And that is a very expensive decision to have to redo.
Absolutely.
So, it really, if you don't bring materials in sooner, it can be very costly.
Yes. Well, we're avoiding that mistake at Kadeya. And so speaking a little bit about Kadeya, you've helped us rethink parts of our hardware system. Now, you've talked a little bit about how you approach supporting startups, building real-world closed-loop solutions. Is there anything that you feel comfortable sharing about what we've worked on together? This stainless steel bottle. I know we're getting a little bit into specifics here, but curious if you can give us an example from our collaboration on how you generally like to work with startups.
So I see closed loop systems in general as about durability, right? Because it has to last, changes over time, but not just some time, a very long time. So specifically with, your system and the bottle and the lid, and as well as all the hardware in the instrument or in the kiosk, that's something that I'm thinking very deeply about, is how to ensure that as the lid itself and the different components of the lid are being exposed to different environments, is actually able to hold up over time. I start really with like systems thinking and just like brutal practicality around these things. So, what conditions are actually realistic? So not just like what the specs sheet says, right? But like, what are we measuring is the extreme temperatures, the extreme humidity, the extreme concentrations of detergents, extreme fatigue. I, in art conservation science, saw a lot of fatigue that you would have never anticipated might happen, but human error is a part of this. So that includes getting a little creative in lab about designing experiments that test that. and the misuse, right? So if a kid is going to use this versus an adult versus someone who's just very busy and doesn't have time and just drops it every 5 minutes, right? I want to design for those different people. And then also, asking, besides the conditions, what are the interfaces where the failure might happen? So where are the seals, coatings, bonds, where dissimilar materials are joining, where that's happening. And then what's the fastest path to getting a known good baseline? Because if you don't have that baseline, then everything is just a moving target.
Yeah.
And it's really hard to design well when you have a moving target. And then lots of changes happen over time. So material failure happens by drift. So that could be creep, swelling, extraction of volatiles or leachables, not typically sudden breaks. So those are all questions that I like to ask, and I'm bringing up in our work together.
Absolutely. I'll just give a kind of small anecdote. Two things. First of all, the very first time we met, right? I had a chance to speak at M-Hub as part of Chicago Climate Connect, and you came up to me, offered, just your expertise pro bono, which was obviously very exciting. But in my position, we actually get offered a lot of services and opportunities constantly. And I asked you a specific question, and you were able to give me a clear answer. And most times I get, this long-winded, this, that, maybe, like you didn't shut the door on other possibilities, but you really demonstrated that very first conversation that you are about moving forward, making progress, taking action, right? Which is something that in the startup world is so valuable, right? You want to fail fast.
Yeah, exactly.
And so it was great to be able to, like, I think I asked you about silicone, and you immediately were like, well, this is what I would be looking for. Yeah. And let's talk about in what location the silicone is going to be used. And so that was like a huge relief. I've been thinking about silicone for 8 years, and then to finally get a straight answer from somebody was such a breath of fresh air.
Amazing.
And then the other thing, just being that, like, we've decided to use a stainless steel bottle, we were able to get to an understanding early on, not having the same training that you do, that our bottles had to be either stainless steel or glass. So we were able to, at least to your point, figure out, like, what is that first thing that we can at least cross off the list. And then we were also able to design the bottle shape and start building the machine around it. But it's really been 5.5 years into the journey that we're now redesigning the cap, and we're able to find you to move forward on what is a really critical next step. And it took that long to kind of build all these other constraints around the bottle to then move forward to say, okay, now what's the cap going to look like? And for everyone who's out there, this is not the final cap. We're so excited in a couple of months to be announcing the new cap design that Dr. Cece has been helping us with. It's going to be beautiful, reusable, very safe, very healthy for you. So definitely keep your eyes open for updates on that front.
And hopefully colorful as well.
Colorful and expressive. Yeah. Yes. We're very excited about all of that work that we've been doing. So, can you talk a little bit about, to your earlier points, about having something to test against? And is that what the word precision means to you? Or if not, explain what is precision and why it's so essential in materials development.
So I love this question, but to me, this is a chemistry question.
Okay.
So this is going back to my early days in Chemistry 101, where we learn very early on about accuracy versus precision, right? So accuracy is all about just like hitting it in the ballpark, right? Just want to get the ball out in the field, get some plays, get some momentum. Whereas precision is really about the difference between a 2-point shot and a 3-point shot, right? And you need to know what you need in order to win the game, right? So if you go for the slam dunk and a 2-point shot when you need a 3-point shot, you don't win. Doesn't matter how great that slam dunk was.
Right.
So that's, to me, what precision is all about in product development.
Is the precision defining in advance that you need that 3-point shot and being clear about that? Or is it being able to measure?
So it's being able, it's both.
Okay.
It's both. You have to be able to measure something in order to know that there is a change existing. So that is a big challenge that I'm really grateful for my material science side of things, because then I can get creative with how to set up measurements that give the information that will give us the answer. However, there's also, if you don't measure something at all and you have a change, you don't know if it's an improvement. And so the way I kind of figure out that reference idea is understanding the difference between a reference and that most extreme worst case scenario. And there might be like 10 worst case scenarios, right? So you have to design for each of those and have references to each of those and have measurements for them in order to understand, if I'm going in this direction, what is that leading to? And then how can I, correct that in those scenarios?
And would you say I'm thinking, of course, about Kadeya, but maybe you have other examples in mind. Are you thinking through how we're going to then be testing and measuring those references on a daily basis in the real world? Or are you doing that more in the lab to stress test in advance?
So I love this question because in my PhD, it was a lot more about just doing it in the lab, right? So in an academic context, it tends to be defined time, defined exposures.
Okay.
In product development, what I really like is we're learning in real time. We have products that are being deployed. We have data being collected that we can get information from in real time. So in this case, what we're going to do is we're going to get the bottles at control reference 0. So time 0. We're going to also pick up as we go and design experiments based on what we're seeing in the real world. So there's going to be some time stamps that we're going to collect that maybe aren't so useful. But we'll find that out as we go. And then design around when it gets worse, so then we know what worse looks like. So it's just about collecting that information over a long period of time, figuring out when is useful, when is not useful, and doing it kind of, we use the Arrhenius equation a lot, which is really just a fancy way of saying, how do we predict 10 years worth of failure, 5 years worth of failure, 1 year versus failure? And so I'm using those models to help predict when we're going to take those bottles and get that data from them.
Cool. So for the Kadeya model, let's say, I'm sure these numbers are totally inaccurate, but let's say we have a hypothesis that a bottle can be reused 5,000 times. So we're going to then set up moments where we are going to test around that.
And we're going to take the bottles out and do tests of them at, what seems like a fraction where you don't expect there to be an issue to make sure and validate and confirm that there are no issues at that point, and then keep taking.
Yeah. And eventually you probably get really precise, right?
And then you can get very precise.
You can be like, actually, it's 5,993 uses.
Exactly.
Cool.
Well, in certain conditions. If the conditions change.
Holding constant. Certain exposures.
Exactly. So different environments where there might have different water chemistries, where we might have different temperatures, things like that. We want to make sure we document those differences. So then we interpret the data. And if we do see discrepancies, we don't overinterpret that difference as an issue, but we see it as it's just a different condition.
Fascinating. I can't wait. Okay. So you said that most product failures are interface problems, not mechanical ones. I love that. I've heard that before. But now I get to speak to the expert. What does that actually mean in practice?
So I see it in a business, if we just kind of high level look at it, material failures just don't happen in isolation, right? They happen at that handshake. When you're interacting and having a relationship with someone, that's where those failures happen. That's why businesses spend so much money in management and working together in relationships with people. We have the same exact thing with materials, where when those materials join, that's where the interface problem will come in. A lot of times teams will talk about those bulk mechanical properties. So like the tensile, all the things that are on the spec sheets, right? And mostly because it's intuitive. It's something you can understand in a very quick way. but also because mechanical engineers tend to lead product teams.
Right.
So there's kind of a bias for that expertise in the data. And when I joined MHub even, I noticed that I was only one of 2 material scientists in this space. So it was very clear to me right from the get-go that there was a missing link to product development in materials. And so these relationships with the failures, what happened like with adhesives when you're joining two materials, over molds, gaskets, coatings, when recycled content, plastics or polymers get kind of doctored into a legacy additive. So when those materials join on, a micro scale, basically, how they interact and then how they fail.
Yep.
Any sort of dissimilar materials when they're joined together under heat or stress, how they fail there. So interfaces will concentrate the stress and the chemistry.
Yep.
And that excessive concentration of those behaviors is what's going to cause ingress, delamination, cracking, contamination.
What does ingress mean?
So like when liquids kind of go beyond a barrier that they're not supposed to.
Okay. Learned a new word today. Okay. That's fascinating. And listening to you talking about the dearth of material scientists in product development, I'm really quickly through my brain rifling through all the investors we've spoken with. And I'm guessing one of them is a material scientist of anyone I've ever spoken with over 15 years in entrepreneurship.
It's a relatively new, it's been around, but as far as offering programs, it is not something that when I was in my undergrad, there were a lot of programs that offered degrees in material science. So it's definitely with the advent of, how polymers have really blown up. A lot of departments have material science departments with polymers have formed. Yeah. And so I think they always say it's like just, plastics was the next century or whatever. And it's like material science is a part of that growth.
Yeah, of course. And now as we're thinking about hopefully moving beyond a fossil fuel future, right? Thinking about what would new materials be that could serve similar functions in our economy today, right? And maybe moving beyond polymers.
Perhaps.
Well, so that's kind of the next topic. Let's talk plastic. Is it inherently bad? Are we going to hell for using plastic? Or if I use stainless steel, do I get into the pearly gates? Or are we overcorrecting based on public perception?
So I love that question. And I see that plastic is not the problem. I see that unmeasured chemistry and unmanaged systems are the problem.
Yeah.
So I was first exposed to polymers through natural polymers. So if you think about art materials of all the centuries, resins, dyes, things like that, they are all polymers.
Yeah.
Early plastics were sustainable polymers. So the reason I was able to transition into sustainable polymer development and products was because of my background in art conservation science, where I was studying early plastics like cellulose acetates. Okay. And that was what I did my PhD dissertation on. And so now it's kind of funny because they were all completely wiped out. They stopped using them. And now it's coming full circle where they're starting to come back. So
interesting. And can you define for us what's a common manifestation of cellulose acetate? What is that?
So it's derived. So cellulose is derived from a plant, and so plastic made of a cellulose isn't necessarily going to be having the same impact on our environment that a petroleum plastic would.
Sure. So like a plant-based plastic.
Exactly.
Okay. Like what we see when you get the compostable cups.
Exactly.
Right. And it says PLA on the bottom.
That's an example. Yeah, exactly. And also knowing that I think this is another thing that a lot of people miss, is that plastic and polymers are not the same thing. So a plastic isn't just one component, it's a heterogeneous mixture. So its majority component is a polymer, and that polymer itself isn't necessarily inherently bad. And generally, they have very stable backbones, to be frank. Complexity comes when you have all these additives that you start putting in, processing aids, degradation products come up, impurities. You usually add about 20% by weight in these different other materials, and they are hugely impactful on the performance of that plastic in the end. And I've seen during my time doing eyeglass lens manufacturing, I saw failures or products fail or succeed really based on additives that are at like 0.05%.
Wow.
By weight. So sometimes at that low percentage, they don't even have to be listed on the SDS. So you're not even, as a consumer or even as a very informed researcher, not even aware necessarily of what is driving the success of that product. And research identifies like over 16,000 chemicals that are involved, right, with plastics themselves. So I really like to kind of bring us back to, instead of this bad or good or what, this binary thinking, I really like to just lead with curiosity around, well, what polymer?
Yeah.
What additives? What exposure conditions? How are we testing it? What is the end of life plan?
Yeah. And why did you select that combination, right? As well.
Exactly. For what application?
Okay. Yeah. I love that. I think that then actually starts to open up also more interesting conversations about systems, about business models, right? If you're moving beyond just saying, well, that material is good or bad, to understand, to your point, like what's the application, what's the end goal. So when you think about public perception today, are we overcorrecting? Are we like maybe in like the first inning of more of a broadly common understanding of plastics? So like the first time you hear about plastics, you're shocked, you're surprised, you didn't know, you start seeing it everywhere, it starts feeling overwhelming. Maybe that's just the first step.
Yeah, I would agree with that. That first kind of step of awareness is a big thing that's happening, right? Where people are just, a lot of us, we grew up with everything gets thrown out. That's how we were raised in this country, right? So, in a lot of the world. So it's really, as long as we have so much single-use products everywhere, when we do wake up to that fact, that is a very hard fact to kind of wrap our brains around, because we're endlessly using and not with an end of life plan.
Right. How do you reconcile consumer concerns like microplastics with actual material performance and health science?
So I truly take the concerns of microplastics very seriously. And I really try to stay evidence-based when I talk about them. We know bottled water has very high particle counts when measured at the nanoscale. We know health impacts aren't fully resolved. We've seen things in fish, we've seen things in animals. We don't fully have a resolution or decision here from the health environment. However, the presence of things doesn't automatically equal harm.
Yep.
But it really does justify that we have better standards. We improve our tests in these materials, and we design to reduce the shedding and exposure from these materials. So I think, like we were talking about, systems thinking around microplastics really does matter. Replacement materials that we might use, they can't just break, shed, or increase emissions by not lasting as long and then needing to replace them more often. So that's like another fear I have with, if we respond to binary about them being bad and we just bring in another replacement product without thinking in a systems like way about it, that also is not going to be great for us long term either.
Yeah, we kind of go back to square one on trying to understand, well, then what's going to be the impact of that? I think about the BPA conversation, bisphenols A, which you'll know better than me, but I remember digging into them for the first time and then realizing that, you get a aluminum can, or you get a stainless steel bottle that says BPA free, or a plastic bottle that says BPA free, but they could be using BPC or BPS. There's all these other bisphenols. To your point about there being 16,000, I guess, additives that layer on top of polymers. So it's like if you villainize one particular material without, I think to your point, stepping back and asking the broader systems question, you just replace one kind of, I don't want to say evil because we're not assuming that, but one material with another one that doesn't necessarily improve the health benefits.
And just displacing one sort of problem for another sort of problem.
Right. Yes, rearranging the deck chairs is my new favorite expression now that I understand what that means. I think that leads really nicely to this concept in sustainability, right? That there's this idea of the perfect material, right? That like if we get rid of plastic, there's going to be something else that's going to save us all. I like to think it might be Kadeya, but stepping back, because Kadeya is only solving one use case, right? One application. There's a huge spectrum of applications that we have to start thinking about. But the reality, moving away from, let's say, plastics or single use, is full of trade-offs. So I know this is a broader concept and it's hard to just summarize for a podcast, but maybe you can share a little bit. How do you prioritize function versus sentiment?
Yes. So from a sentiment perspective, I am not a believer in a perfect solution in general. Just like when I hear about a perfect investor or a perfect inventor, I generally find that to be based in hype rather than a full picture of what's going on. And it generally makes me wonder, what is the flip side? What do we don't know yet? And really it makes me think about entropy, right? For every positive, you have an equal and opposite negative. So that's something that I'm always thinking about in this space. And, fire retardants being a great example of that. Right. So I really try to think about it as a multi-objective optimization of safety, performance, durability, manufacturability, and sustainability. And then asking the major questions around what are the dominant risks? What is the chemical exposure? What is the dominant mechanical failure? How do we repair this? Is that possible to repair this and have it in a cyclic way? Is there a supply chain barrier to making all of the above happen? And then also acknowledging that natural things aren't necessarily always safer. I grew up with parents telling stories at the dinner table about the medical field, and a lot of times I recall hearing my mom reflect on, they didn't tell me about this medicine they were taking because it was herbal, and they thought it wouldn't affect their condition, but it did. And how heartbreaking that was for my mom as an internist, because people assumed that it was natural, so it wouldn't impact things and it wouldn't be bad. But in the long run, whether it's from a pharmaceutical or it's from, earth in a beautiful way, everything is going to interact in some way. And it's about understanding that interaction. And also understanding that compostable is not necessarily going to be lower impact either, because the greenhouse gases of that, if you have to reuse it more often, there's also that possible failure that will cause an earlier waste. So I really think about the most sustainable material being the one that actually survives that real use case and doesn't harm us further.
Yeah. And going back to the reference you made to fire retardants, do you want to explain why that illustrates?
So, putting out
an imperfect material.
Yeah. So then so it's really referencing PFAS, right? And the byproducts of that in the environment, and how that is a forever chemical that, even though it's great at destroying fires that can hurt us, it also is poisoning us. So,
and
not a silver bullet there.
Yeah. And I don't mean to go too much down the rabbit hole, but I think PFAS is on people's minds a lot. People are also becoming more aware of it. EPA, under the previous administration, had said they would start monitoring and measuring 6 types of them. Now that's been rolled back. So I think people are starting to ask questions in a similar way that they've begun asking questions about microplastics. So when you talk about like fire retardants, if you could go back 30, 40 years to when those were being developed and then commercialized as a material scientist, what would have been the test? That or is that one of those questions of time that you can't predict and test for?
So I think you can always, if you have more time, if you put more time into your product development to measure things long term, which a lot of times that was the biggest learning curve I had adjusting from academia and our conservation science to product development, was realizing that a lot of these longer term properties beyond that expiration date is not tested. So when you use something beyond its expiration date, it doesn't mean that it doesn't function anymore. It means it probably is not safe for you to function with it anymore.
Okay.
So a lot of that testing is not done. And so if you put more time, if I went back 30 years and asked those questions, I'm not sure anyone would listen to me as a woman in that space, but asking those questions about how it's going to interact, how it's going to impact the environment, those are things that could be brought and could be measured.
And probably were not. Or if they were not,
I would have to dig in to know exactly who ignored what at what point.
Okay. Cool. We'll leave it at that. So actually, that's kind of interesting in terms of this question of balancing product vision with material limitations, right? So in the Kadeya case, we've talked about glass versus steel versus plant-based plastics at Kadeya. For us, it was a kind of, in retrospect, an obvious aha moment because we were going after industrial workplaces that glass just wouldn't work. So like that's an early example where we should have maybe foreseen that problem. Yeah, in retrospect. I don't know if you have anything to add in terms of balancing product vision with material limitations.
It's something you have to learn at the beginning.
Yeah.
And I think that there's just no wrong question to ask at the beginning. That more questions means you're thinking about more things. And then when you get to the point where we have to make that call, you've already thought about it and considered the benefits and risks either way.
Yeah. You wrote recently about the 5 questions that prevent 30 to 70% of product development waste. Which of those do founders most often skip?
So I love that you saw this post because this is one of my recent favorites. And again, I think the most expensive failures come from questions that people are not going to be asking early enough. So just to review for everyone who is not following my LinkedIn as closely as you are, those questions include, what problem is being solved and for whom? What environment is it facing? And is that really, are you using that as spec sheet or do you know exactly, have you measured what that environment looks like? What materials and interfaces carry the load? What data is needed before advancing to manufacturing? And what assumptions are there that will break at scale so you're ready? So I find a lot of time in product development, I hear people addressing, question 1, because if you don't have the product market fit, you're going to fail pretty quickly. I hear people talking about environments. You're going to have unhappy customers and recalls if you're not addressing that question. I find with my clients at CArtLab Solutions, what we do is we really dig into 3 through 5. So auditing materials, defining the right data that needs to be measured, testing the assumptions that may come up during scaling. So it might feel slow when you have to slow down production to answer those questions and collect that information, but it really is something that can save a company long term.
And it allows you to accelerate later on.
Once you have all that information, I think you really will get much further as a company.
Yeah, we hope so.
Yep, that's our goal.
We're investing in that up front. So for the listeners out there who would like to have a clear takeaway from your incredible wisdom, what should people actually be asking when they buy, evaluate, or regulate materials for safety?
So I believe that safety really does live at the interface of hazard and exposure.
Okay.
So 3 main brackets of exposure. So touching, breathing, tasting. How long, what concentration. Our noses are great. They smell things at very low concentrations. So trusting that scent and at what temperatures. Then there's the chemical complexity. So what variability specifically in the additives of what you're looking at by the suppliers are impacting you. So that's the variability you might see from one batch to the next.
Okay.
And then durability, how does that change with time and just human use?
So I have a specific example in mind, like going to the supermarket and buying some like window cleaner. Like, how would the average consumer start to interpret what you've recommended? Or maybe you have a different example of something that you interact with pretty regularly as a consumer, shampoo or hand soap. Or maybe you have a better example.
I'm trying to think of a good example. One thing it keeps popping up to my mind right now is really just like my vegetables.
Yeah.
So I'm always thinking about my vegetables and washing them and the pesticides in them before I pop them in my mouth and enjoy them. So one thing that I always do is think about, well, what is doing a little research around, okay, if I can't get organic, what might be there? And doing a little research on that. And one thing that when I did do research on that around pesticides was that a lot of times they tend to be acidic. So when you go to the grocery store and you're buying like this, Trader Joe's sells this great product that I love, but it doesn't help because it's acidic. So it doesn't get rid of those pesticides. So what I do is I have like a baking soda solution in my kitchen that I put on all my fruits and vegetables before I eat them. And then I know, okay, well, whatever was there, I neutralized the pH so they washed away with water.
Wow.
So things like that, I try to just do a little investigation and then find a solution. And again, I have a lot of did you know posts, so I'm going to hype my LinkedIn right now, where I talk about these kinds of things for people to think about, because not all of us are material scientists that understand when they do the research what that actually means for solving it, right?
Yeah, incredible. Okay, we're going to include that in the show notes, linking to your LinkedIn, as well as maybe we could get your baking soda recipe.
Yeah.
For washing vegetables.
Yeah. I mean, it's a very basic solution, but I'd love to share.
Okay. Literally basic. Yeah. Okay. That's like my high school science nerd coming out. Okay. And last question before we go into rapid fire. If you could wave a wand and change one thing about the way the public understands material safety, what would it be?
I would try to help people see that materials aren't moral. There's no moral complexity to them, but there really is the ability to measure them.
I love that.
So replacing that binary thinking with dose and context thinking.
Very cool. Well, from that, let's go into the rapid fire. What's one material people totally misunderstand?
So you did tell me when we first met, this was something you had been thinking a lot about. And it's because it's something that people do misunderstand, which is silicone. It really, silicone material versus silicone the element, first step, right? Okay. People mistake that all the time. And then it will vary a lot by formulation, how it's processed, what it's processed with, as well as the environment that's in.
Yeah, interesting. I've been learning a little bit more about like silicone for like my son, and his food grade products. Okay. What is the most exciting emerging material that you've tested?
So I'm going to push back and not say emerging material because my most exciting materials I've ever looked at are actually nature-based.
Okay.
So the most exciting material I've ever looked at under a scanning electron microscope is a morpho butterfly wing.
Whoa.
It has photonic structure, so it's structural color.
Okay.
So the color is not based on like absorbing light. It's based on how the light reflects off of it. on a
Very
nano
cool.
scale. So
Because of the geometry of the
so
wing?
it basically at every single level you go down from macro, micro, nano. It looks different. It's not the same.
Wow. What's the worst everyday product design that you interact with from a materials point of view?
So dishwasher safe multi-material products that don't have interface design.
Okay.
So that's pretty much like any cookware that has that says it's dishwasher safe but has like 5 materials. So one thing I think about a lot is normal water bottle lids.
Yeah.
I do not put those in the dishwasher.
Yeah.
We have a whole list of things in our house that are not allowed to go in the dishwasher.
Yep.
And we hand wash them.
Yep. Yeah, I learned recently, and I don't know if this is the exact illustration of what you're saying, but when you have an insulated or double wall stainless steel bottle, it tells you not to put in the dishwasher.
Mm-hmm.
And the reason is because of the seams, right? One of the reasons is that maybe you can.
There's a lot of reasons, but
Okay.
yeah, but that is definitely a great example. But that one they will tell you is not dishwasher safe. There's a lot of things
Right. At least they tell you that.
Yeah, there's a lot of things that they say, oh, this is dishwasher safe utensil, right? And it's like a it has a grip on it or an overmold on it. It's just not meant to last. We have these tongs that my husband loves, and they have they're just not made to be put in the dishwasher, even though they're stainless steel and rubber that separately might be okay. Together, it's just they fall apart, and we always have to buy new ones.
I can see a Dr. CC e-commerce site coming up soon. Dr. CC recommended. What's one consumer habit you wish people would rethink?
This is something I think a lot about for my grandma, actually, who's 95. And one consumer habit that I'm telling her all the time is stop reusing your single-use containers. Stop reusing them. I know you don't want to throw it away. That is the system that we live in, and you need to throw it away and use something that is meant for reuse. Yeah.
Or if you're going to use it for something entirely different, like potting your plants, maybe.
Entirely different.
Yeah.
Yeah.
Or storing your...
Don't keep refilling that water bottle.
Yeah. Yep. Please don't. Please, I know. I tell people that because they're like, well, I'm being more sustainable. Yeah. Okay. So what's in your cup? Is it ceramic, stainless, or glass? And why?
So my whole philosophy, as you might be able to tell from this conversation, is it really depends on the use case. So in the use case of my favorite latte, I will always have a ceramic container. If I'm on the go with water, I like stainless. I like the vacuum sealed stainless interior bottles with plastic on the outside because they keep my water really cold. And I'm an ice queen. So I do love having ice in my bottle as well. So I love those too, but it really depends on the context. And then also glass at home.
For regular beverages.
Beverages or just storage of like soups and things like that.
And that glass includes Pyrex.
Yes.
Okay.
Yes.
Cool.
Even though my mom always asks me when she has to replace something, are you sure it has to be Pyrex? It's more expensive. And I say, please just do it. You won't buy it again. You won't need to buy it again.
You use it for your whole life.
Yeah.
All right. Very cool. Thank you so much, Dr. CC. I have learned so much. I hope everybody else has learned a lot as well. We'll be including great references in the show notes so that you can continue to follow Dr. CC, learn from her incredible expertise, and keep an eye out for Kadeya's new bottle cap design that we will be revealing in a couple of months. Thank you. Thanks for listening to Unbottled. If this episode got you thinking about plastic, systems change, or how we build a better future, don't just be a listener, be an owner. Kadeya is raising a community round on WeFunder, and that means you can invest as little as $100 and help us bring closed-loop beverage systems to more people in more places. Because real change doesn't happen alone, and the future of hydration needs all of us. Learn more and join our investor community at wefunder.com/Kadeya. That's Kadeya. The link is also in the show notes. Let's build it together.